I want to draw a picture of a hill with a little car on top of the hill. You're going to recognize this for Physics 20 because we do a lot of these in Physics 20, whether you were in my class or Mr. Coder's class. Those roller coaster type problems, right? When you see this, what's the first thing that comes to your mind in terms of a strategy? You don't even know what you're being asked to solve for here yet, right? But we know that, Eric, we're going to do probably conservation of energy, right? So we're going to say probably EI equals EF. The initial energy equals the final energy. Some people might say EA equals EB. Some people might say, E top equals E bottom, or it amounts to the same thing, right? EI equals EF. If I start off up here at the top of this hill at a speed of 0 meters per second, and this car rolls down a hill of height, let's say 20 meters, what kind of energy does this car lose as it goes down the hill? Good. It loses potential energy. It's going to be specifically gravitational potential energy as it goes down the hill. What kind does it gain as it goes down the hill? Kinetic energy, right. It loses gravitational potential energy because it loses height. It gains kinetic energy because it speeds up. And what doesn't change? Well, the speed changes, the velocity changes because kinetic energy increases. The speed or velocity is going to increase, right? What doesn't change, Spencer? The total energy doesn't change. The total energy will remain the same. And that's why we can set in this question EI equal to EF. What would be my next step in this question? Yep. Yeah, okay. So what kind of energy do we have at the top and the bottom? And then let's write down the equations for them. What kind do I have at the top if this car has a height of 20 meters and is not moving? Gravitational potential energy. So we'll sub in MGH, initial for this, equals, no kinetic at the top, right, because it's not moving, equals what at the bottom? Kinetic energy because it's moving, so it's going to be 1/2 mv squared. Do I have a height at the bottom? No, so I don't have any kinetic energy, any potential energy at the bottom. Does that make sense? It's amazing how the first day we do this in Physics 20, people are like, what, when do I put that equation in? But now this seems easy for the most part, right? This seems pretty easy. All right. Well, I'm going to draw another picture over here now on the right-hand side. This time we're going to have a positively charged plate and a negatively charged plate. And I'm going to introduce, right beside the positively charged plate, a positive charge. Proton, alpha particle, whatever, it doesn't matter. It's positively charged. It has a speed of 0 meters per second. So it's just placed in there. Well, it could be like the electron that's just below the cloud that is negatively charged before lightning begins to strike. Except it's positive, below a positive cloud. What happens to that positive charge? It's going to accelerate downward, just like the car accelerated downward down the hill, right? It's going to speed up as it goes down the hill. What kind of energy would this car have at the top of the first hill? You already told me that it was gravitational potential, right? What kind of energy would this charged particle have before it began to accelerate? Somebody said it? Electric potential energy, right. So what kind does it lose as it speeds up, gets attracted toward the negative plate? It loses electrical potential energy. What kind does it gain? Charged particle speeds up just like the car speeds up. Car gains kinetic energy. The charged particle gains kinetic energy as well. What doesn't change? The total energy. The total energy will remain the same. Therefore, we can absolutely say, just like we did for the car going down the hill, EI equals EF. Now, here's what I want you to do. Whenever you see a question where a charged particle is speeding up or slowing down, but we'll deal with the speeding up ones right now. Charged particles speeding up or slowing down, I want you to think of it as a car. When a charged particle speeds up, that's like a car going down a hill. So solve the problem as a car going down the hill. Here's a car at the top of the hill at rest. What kind of energy does it have at the top of the hill? MGH, potential energy. What kind does it have at the bottom of the hill? Kinetic energy, 1/2 mv squared. We pretended it was the car going down the hill. But the reality, of course, is it isn't. So we need to replace mgh with an equation for electric potential energy. And that equation for electric potential energy comes from this one that appears on your data sheet. Delta V is equal to delta E over Q. Yesterday we said potential difference was related to energy. Today I want to give you a little bit better, a little bit more specific definition for that. Energy is like arms. If there's 30 of us in this room right now, how much energy do we have? 60. Does that make sense? Okay, well, how many arms per person do we have right now? 2. So energy is 60, potential is 2. Does that make sense? Energy is the total, the potential is the energy per person. Or when we talk about electricity, it's the energy per coulomb of charge. Potential is energy per coulomb of charge. Potential difference is the difference in energy per charge. So this is where the analogy falls apart a little bit. Okay, if somehow we walked into class tomorrow and each of us only had one arm, then our potential difference would be 1. Because we had 2, now we have 1. Our difference in potential was 1. That make sense? Now, you want to find an equation for electric potential energy? Take this one and rearrange it. E is equal to Q times V. It's charge times electric potential. Potential, remember, the energy per coulomb of charge. And let's replace that mgh with that new equation for potential energy, Q times V. Remember, that's a capital V, though. It's not Q times speed. It's Q times potential. It's Q times 2 arms. Q times V, the charge times the potential, is like saying 30 people times 2 arms gives me a total potential energy of 60. Okay? So strategically, again, you see this problem, charged particles speeding up. Even if you don't see a picture, think, oh, that's like a car going down a hill. What kind of energy does a car have at the top of the hill? Potential, mgh. Well, let's replace mgh with qv. What kind does it have at the bottom of the hill? 1/2 mv squared, kinetic energy. All right, sub in 1/2 mv squared. Same question, except we're replacing mgh with qv. Let's change this question a little bit, though. Let's now say that this car does have a speed at the top of the first hill. Let's say that this car has a speed of 10 meters per second up here. Say that this charge over here has a speed of 10 meters per second. What kind of energy does the car have now before it starts? Top of the hill. It's got potential energy still because it's got height, but it's also got kinetic energy because it's moving at the top of the hill. This is like last year when you went to West Edmonton Mall for your field trip. The Mindbender cart goes over the top, and it's moving a little bit at the top of the first hill, right? It had potential energy and kinetic energy a little bit at the top of the first hill. So mgh plus 1/2 mv squared equals 1/2 mv squared. What about over here? mgh plus 1/2 mv squared, because it's got an initial speed, equals 1/2 mv squared. We just replace mgh with qv. 30 people times 2 arms gives me a total of 60. Or Q times V gives me the total potential energy. What if I was looking for the speed of the car halfway down the hill? Or what if I was looking for the speed of this positive charge halfway across these plates? mgh plus 1/2 mv squared doesn't change, right? What do I have over on the right-hand side? Halfway down the hill, 1/2 mv squared because it's moving, right? Plus mgh, final. What would the final height be? The initial height would be 20. The final height would be 10 meters, right? We solve for VF or whatever it is that you're looking for. Well, what if I wanted to find the speed halfway across here? What kind do I start with? Potential and kinetic. Except potential is QV. What kind do I end with? Potential and kinetic. Except potential is QV. Now, if the initial potential here was 20 and the final potential was 0, then we would say VI is 20 and VF is, what is it? Halfway across, VF is 10. So your potential is like your height. It's your height that contributes to your gravitational potential energy. It's your potential that contributes to your electric potential energy. Does that make a little bit of sense? Let's do an example. You have this example written down for you already in the handout that I gave you. It says the electron is released at a speed of 1 times 10 to the 5 meters per second at a negatively charged plate and accelerates toward a positively charged plate. So this is an electron. Like, read this first sentence carefully, okay? This is an electron that's released at this speed and accelerates toward a positive plate. Is that going to speed up or slow down? Speed up. That's like a car doing what? That's like a car going down a hill. So picture it now. Picture a car going down a hill. I don't know about you, but I can't see an electron accelerating towards a plate. I can see a car going down a hill. I can visualize that, right? Matt, can you visualize that? What color is the car? Okay. How many people are in the car? Old or young? Yeah? Is there any rust on the car? No, is it a truck or a car? Okay. Like a new car or an older car? Good. Visualize the car. Know what the car looks like, right? You can't do that for an electron. It's a lot harder to visualize it because we've never seen it before. So we picture that car going down the hill. And when that car goes down the hill, when we picture it going down the hill, we know that it starts off with potential energy, MGH. And it also starts off with kinetic energy because it was moving at the top of the hill. Oh, wait. It's not really gravitational potential energy, is it? Because we're not really talking about a car going down a hill. It's really electric potential energy. But otherwise, the question's exactly the same. Now, when the car has gone halfway down the hill, what kind of energy does it have? Both. It has MGH, and it has 1 FmV squared, potential energy and kinetic energy. But it doesn't really have gravitational potential energy. It has electric potential energy. But otherwise, it's exactly the same. Now let's sub in some numbers, and let's try to find the value of speed. This is the one place where I suggest that you sub in numbers first before you rearrange. The charge of the electron is 1.60 times 10 to the minus 19 coulombs. The initial potential is 20 volts. The mass of the electron on my data sheet, and the initial speed is 1 times 10 to the 5. The charge, once again, is 1.6 times 10 to the minus 19. What would be my final potential here? If the potential difference between the two plates, the difference between the two plates is 20, then let's assume that one side is 20 and one side is 0. Okay, does that make sense? Like if my difference in height is 20, then we'll say the top of the hill is 20 and the bottom of the hill is 0. So if the top of the hill is 20 volts, what's halfway down the hill going to be? 10 volts. Plus 1/2 of 9.11 times 10 to the minus 31 times VF squared. Now, a little bit tricky mathematically here. Let's get the left side. 1.6 times 10 to the minus 19 times 20 plus, use some brackets here, 0.5 times 9.11 times 10 to the minus 31 times 1 times 10 to the 5 squared. There's my left side. And now let's take this term over by subtracting Use some brackets there. 1.6 times 10 to the minus 19 times 10. And then let's take the half over by multiplying, times it by 2. Take the 9.11 over by dividing. And I got 3.5 times 10 to the 12 meters per second. Sound good? The biggest speed you can ever have is 3 times 10 to the 8 meters per second. You can have whatever acceleration, but not whatever speed. This is too high. What have we forgot to do? Square root it. If you ever get a speed that's 10 to the 12, 10 to the 13, 10 to the 14, it's almost certainly because you forgot to square root it. Oops. What's this, Matt?
No way you said square root.
So we get 1.88 times 10 to the 6. Which is perfectly reasonable. Usually, that's a really common speed for a charged particle. 10 to the 5, 10 to the 6 meters per second. Could be a little higher, could be lower, but that's right in the range that we usually expect to see. What about when it's going all the way across to the negative plate? Well, that's like the car going all the way down the hill to the bottom. The car at the top of the hill has potential energy, MGH, but we're going to replace that with QV. It also has kinetic energy. At the complete bottom of the hill, the car only has kinetic, no potential, because it's got no more potential to fall. We're going to say the charge here, again, is 1.6 times 10 to the minus 19. This one's easier. VI is 20. Sure, that should be a VI. This is easier because we don't have a VF, right? We're at the bottom of the hill. Potential is like height. At the bottom of the hill, we have no height, we have no potential. So the next time a teacher says to you, you have no potential, all they mean is that you're at the bottom of the hill. So you have no ability to fall any lower because you're at the bottom, you're not up on a hill, right? They don't mean anything bad by that. Just that you have nowhere to fall because you're on the ground already. Now wait. If you happen to be on the roof of the school and your teacher says you have no potential, well then they might mean something a little different by that then, because you do have potential energy then. Okay, let's calculate this. 1.6 times 10 to the minus 19 times 20. Let's add to that 0.5 times 9.11 times 10 to the minus 31 times 1 times 10 to the 5 squared. There's my number on the left side. Now let's times that by 2. Oops. My answer times it by 2. Let's divide that by 9.11. Times 10 to the minus 31. And then let's 10 to the 12 again. Must be I forgot to square root. So let's square root that. 2.65 times 10 to the 6. Yeah. We got a bigger number than we got last time. Does that make sense? Yeah, car is moving faster at the bottom of the hill than it is halfway down the hill, right? Yeah?